Hey, what's up? In this video, we're going to be taking a look at how we can find format string vulnerabilities and compiled binaries. What we really want to talk about is kind of like the process of breaking this down and trying to find it. And this is what we're going to be building. So this is really nice, but how does this actually work? And what are some of the things that we're looking for? What are some of the things that we can't find? You know, things like that. That's what we want to take a look at tonight. I have a repo here called Potentially Vulnerable. Potentially Vulnerable is just a set of random scripts for looking at things. So we did a couple of videos on CWE78, which is OS command injection. And we did Inghidra and Binary Ninja. There's a sample binary here that you can take a look at that has stuff. And then we also are going to be doing the same thing for 134. Right now I'm working on the Binary Ninja one, but I'm sure at some point I'll do a Inghidra one and throw it up here as well and kind of update this. There's also a bin. This bin comes from the Juliet set. And I'll tell you what that is in just a minute. I put this up here. It's an x86-64 ELF. And the reason for that is just because it can be kind of a bear to compile all the source code for that just to get a sample test case. So I wanted to give you something to play with if you are interested in trying this out yourself. Now, the test set that we're going to be using is one binary out of many that can come out of from the NSA Center of Software, NSA Center for Assured Software. I always thought it was software assurance. So it's a little over 64,000 test cases for C and C++. Then what we can do is run those in analyzers and try to figure out sort of if we can find these problems. They have a really nice naming convention for this, where if it's underscore bad, then you know that you found something that's particularly bad. If I look at the extraction, so if I go and download the Juliet test suite for C and C++, we'll have this whole test suite extracted. Then you'll have a C directory, go into that, and test cases. These are all of the CWEs, or common weakness enumerations, for all of these. The ones that we're worried about tonight are uncontrolled format strings. So there's quite a few of them here. Some of these later ones I think only pertain, they might all pertain to every single system. Some of them are like Windows only, and they'll have if-defs too. So using parts of the Windows API versus, POSIX compliance or something, depending on what you compile for, will utilize different pieces of code, right? So we're going to be taking a look at specifically this SO1, and this 134 SO1 is what I had back here inside of the bin directory. And again, that's for an ELF. But the differences in code that you can get just by switching compiler version, optimizations, and platform. Visual Studio does some really crazy stuff with function wrappers and a lot of really weird stuff that you just don't see in Linux or when you're compiling with GCC. So I think that's pretty interesting. Here's a PDF from a Stanford class. It's pretty interesting. Like, the only time, like when I learned about format string vulnerabilities, I learned this, right? So I'm just looking for things like printf or fprintf or whatever else, and data that comes from a user. The question is, do you alert on a function like this? And it's like, I don't know. I mean, it really depends, because there's only one parameter being passed to it. There should be at least two, and that is you have a format string with a format specifier like %s, and then you have some variable, right? It's okay that this is user controlled, right? Because it's being parameterized and passed in and formatted correctly. The problem with this here is I can do something like %x and actually pop data off of the stack and leak data from the stack. You can use %n to then give you a primitive write what where. Let's take a look at what this thing is doing to find this. So for example, if I go to this one, 11, for example, I'll get this address, go in Binary Ninja here, and I am in high-level IL. So this var A1 is what I'm interested in. I can just kind of scroll in on here. And then what I want to do is track this up and see where it's been used. And then bam, right here on a receive, a buffer in. So I've set this up and declared this, whatever this is, it's a buffer somewhere. And when I receive off that socket, it's going straight into here. There is this RAX3 that adds to this. And it turns out if you look up a little bit more, that's from a string length. And then this is from var78, which is just a null string. You have nothing there. So all we really need to do for this pattern is to look for printf functions, right? Or any other format string function, and look for the parameter that is the actual format string, right? In this case, there's only one parameter that should be an alert already. Like, this seems weird. I should have multiple in a printf. We'll get var a0 or whatever var is passed to it, and we'll go see if it relates to a source of data that we care about. In this case, receive, the second parameter, even if it's manipulated in some form, is still interesting to us, and we would just alert. And that's exactly what this is doing. So let's stop talking about that and just try to figure out how this actually does it. So a couple interesting talking points that one will look at is the differences between MLIL and HLIL. Now let's go ahead and take a look at sources and sinks. Okay, so these are some of the format string functions that we're interested in. These are two of the sources that we're interested in, right? Data can come from basically anywhere. We can consider, just like in this example, the source of data is actually just a parameter passed in to the function, like as a function argument. So in that case, we don't know if it's user controlled. What we'd have to do is find all the callers of func and see what they pass to it and analyze all of those individually. We could just simplify it and say, yeah, if I get data passed in on the function, I'm just going to assume that it's user controlled and alert if this ever gets the case. That way, if you're scanning a binary and you find it, as long as you're not finding like 50,000 of those where it would just take way too much time to check yourself and verify, what's the harm, right? Just go ahead and do it. All right, so getting back to this, these are the ones that we have. I have a dictionary here, and then the key in each dictionary is the source, and then the value for that is the parameter index for the thing that we care about. So fgets, for example, we care about the string. For receive, we care about buffer, because that's where the data is actually going to come in. That's what we care about. The len, the flags, things like this, we don't necessarily care about. We want to connect this string and this buffer to the format specifier or format specifier location here. So in printf, format exists in the first index into that array, which is 0, so it's a 0. For sn printf, it is 3. So being 0 indexed, it's 2, right? So that's what we're doing. We have a debug print function, which will be helpful soon. So the very first thing we do, we're going to import Binary Ninja and argparse. Binary Ninja, open view. We give it the target that comes from argparse, and we open it as a binary view. So what we're going to do is, the very first thing is to find all symbols we want to analyze. So to do that, we'll create an empty symbols list, and we'll say, get all symbols by name for this sync. So we're basically saying, is there anything that looks like printf, right? Is there anything that looks like fprintf? We put all those into a list, and then we check to see what type it is. So there's different symbol types. The ones that I care about are an imported function symbol. Then I'll append those to the symbol list, and if that symbol list comes out to be nothing, then I'm going to continue on to the next sync and keep going. So once we have this list of symbols, and these are symbol objects, right, not just names, we're going to go figure out who calls those things. So rather than looking at every single function to say, do you call the symbol, do you call the symbol, what we'll do is find the symbols and then go find just the only places where those are called and analyze those, okay? So we have all these symbols. So for symbol and symbols, we're going to do get callers, and we'll give it the address. This will give us all of the callers. If there are no locations where that symbol is called from, or we can't resolve any, then we go to the next one, right? And then for every caller in these callers that we found, we're just going to get the function object and the address for it. That's going to allow us to get an MLIL index. So we need to basically find the location where each of these things are called. So we might have found that printf is called in 5 different locations, and Binary Ninja is really good at telling us, hey, this function A and function B call it. I'll go ahead and get the MLIL function. The reason why I'm doing this is that there's no get instruction start for HLIL, so I have to go to MLIL first, get that index for the instruction of where the call is made. You can index straight into that to get the MLIL instruction. So let me show you what that looks like. 7, let's say. All right, that's this function right here. It doesn't resolve the name in this output, but this is it, okay? So that's exactly what we're doing when we say MLIL index. We got the index from this from the address. Then we go ahead and get the instruction, and then we get the HLIL version of that instruction. So then we'll get a list of params, empty. We're going to see if that instruction is a call instruction. If it is, we'll get all the parameters. Now we want to isolate that format parameter, right? So if we look back up at our syncs, the format parameter that we want for fprintf is at index 1. For snprintf, it's at index 2. For printf, it's at index 0. So this is what we're doing. We're going to isolate that. As long as the number of parameters is greater or equal to that, I know I'm safe indexing into that location without having an exception thrown, right? So that's the reason why I do that. So in parameters, we'll do the sync, which will say, if we're looking at printf, it'll just give us a 0. So this will resolve to 0. I'll get the 0th parameter, and that'll be my fparam or format string parameter, okay? Then I'm gonna get the expression type. So if expression type exists, right, and it's a constant, then I'm gonna go ahead and just say it's safe and move on to the next one, right? That's the idea. If I have a printf and the only thing that's passed to it is an actual like static string that is hello world, then there's no reason to look anymore because nothing can be manipulated or affected there. So we just say it's safe and move on with our lives, right? So for this target var, what we want to do here is get the actual variable that's at that location, okay? So we'll get the actual parameter, but depending on what type of parameter it is. So let's say, for example, this is a variable, but if we look down, like this is like a constant. Of course, I don't see any right now. So here's the deref, okay? So if we look up here, we're gonna look to see if it's an HLIL deref. If it is, then I need to do param source var. If it's just a high level variable, then I just need to do fparam var. So that's the way that's gonna allow us to pull this out. I also have a little debug string in here because under testing, while I'm doing this, I'm really only seeing vars and derefs, but I know that if I point this at some other binary that I had never tested before, it's inevitable that I'll find something that's not a var or deref. Maybe it's a call or something that's then, resolved and then put at that location. So what I want to do is have this else case that says unsupported type. That way, if I'm doing maintenance on this script, I can change this to a true, run it, and then I can see all the errors that are coming out. Like, hey, listen, at this location, you don't actually support this type. You better add it. Okay, so number 5, we're gonna locate the definition and initialization for all of these things. So what we're essentially doing now at this point is finding our sync, and we're gonna say var a0. I don't wanna go through this entire function looking at every single instruction, trying to find out if it's related to this variable. Instead, you can ask Binary Ninja, like, hey, tell me all the locations where this is used. So it'll give you this, 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 but it will not give you this because this is the definition, not a use. So what we have to do is we can do get var definitions for the target variable, and our target variable is this var a0. And then there's uses, so give me all the uses where that's used. And then we get definitions and uses. And I just had this in a debug print. When I was just starting out with this script, I printed all of those out just to make sure I could kind of see everything and things sort of made sense to me in the script. Then when I felt pretty confident with them, I put them in a debug print. So we're gonna loop over all uses, and we're gonna say, is the use a call, okay? If it's a call, we're gonna do something. If it's a var init, we're initializing the variable. Then we're gonna do one thing. And then you start to realize, like, as you start testing these things, there's different things that we need to kind of drill down towards, and you can build this up. So let's take a look at the first one. The first one is if the use, and again, this would be use down here, okay? So the use on this one is gonna be like a variable assignment, okay? And we can do that by saying, let me go ahead and clear this. Current HLIL, and then I'll do 24. All right, and then I'll do operation. All right, so that's a var init. Okay, so this guy would end up be a var init. So up here, we would end up hitting this part because the use, the instruction at that use, its operation is a var init. Okay, cool. So now what we need to do is kind of unwrap that onion and try to figure out like what we're looking at here and seeing if it relates to our sync variable, okay? Or wraps back to a source, I mean. So we want to find the call location, source call instruction. So this is the source. So looking at source and destination, if we do that right now, for this guy, we can do this operation. If we do source, it's like here's the actual instruction, here is the source, and here is the destination. Yeah, so the destination, so for this guy, this is a var init. So let me go look at a var init. This one is a var init. If I did the instruction current HLIL, I'm gonna give it 24 stirchar. So basically I'm looking to see if we can resolve this location, where are we actually like going back to, right? So that's from this as well. So we want to know if we do this, is that source actually being, what do you call it, referenced in our track sources. All right, so quick edit there. I actually had a little bit of a bug in here, a weird case of kind of a copy pasta from something I saw before, so I'll fix that on the repo. Essentially what we have here is we have this var init, and this is one of the things that can really bite you, is if you're writing this at a specific binary that you know is vulnerable and you're writing a signature kind of for it or a pattern for it, you can make certain assumptions that like this is always the case that this is going to be, and then you run it on a different target and all of a sudden you're getting exceptions because you're referencing a wrong type or something like that. And in this case, this is kind of it. So there's an HLIL var init if I get to this instruction and its operation is a var init, and then I sort of assume that it's just a call, right? So I do the use, the instruction for it. I already know that if it's a var init, it's going to have a source, like where is that coming from? And then I get the destination, and that destination from that source, if this is already a call, so this is not just a call, like for example, this is a call, this is a var init with a call, okay? So that's sort of the subtle difference here. What I should really be doing probably after this line is then checking to see if use, instruction, source is of type, source operation is of type HLIL call, and if it is, then isolate sort of like where that's coming from in sources. And I haven't gotten any exceptions yet, so I just kind of roll with it, YOLO. But that's one of the things that can bite you, is like this kind of case where, I wrote this and I looked at this and I didn't see or notice that until I just started talking about it now live with you. So, okay. So anyway, if this turns out to be a target to a certain source, we go up here, and if it ends up being an fgets or a receive, then we keep looking at it. What we're gonna do when we keep looking at it is we're gonna get the call instruction. So we'll get that source, it's the call that we're going towards, and then we get the parameters from that, so everything that's passed to it. So for example, this strchr would go and get these two guys as the parameters for that. Once we have those two parameters, then we're gonna add one to it just to account for the zero indexing, and then we're gonna use that length of the parameters just to make sure that we're not gonna screw up here and be outside of the range of a valid index inside of params. So we'll get that target param index. So we go to sources, get that destination. So let's see here. Yeah, sources, the name for it, and this will return the actual index. So in that case, it's like if this were fgets, it would be a 0. If it were received, it'd be a 1 that got returned from this. So paramdex would be 0 or 1. In that particular case, now we do params, get that 0 or 1, put it into target param. Then we look through the prefix operands. So for P and prefix operands is sort of a way to kind of like peek into everything without having to like write all the code to drill down into all of it. So in this particular function, if I'm doing current HLIL 24 here, I can do prefix or postfix operands, right? And then that gives us everything that is listed in here, like all of the components that build this instruction. And we could go through each one of them and see if there's certain types or whatever we're looking for. In this case, I use for prefix or parameter or whatever. In each one of those operands, I get P, and then I say if it's a variable and that variable is equal to our target variable, then we're going to alert. So we just try to see if it's in there. It's a simplified way without having to pull apart every single possibility, which would be like, here's a var A, and then it would either be var A or this is an addition with a var A, so I need to drill down into that addition. If it were a subtraction or some other operation, this could even be like a call that resolves the buffer and returns it. Like, there's so many different things that can end up being here that having to parse all that stuff out manually, it just seems like a lot of work. Definitely possible, but I think this is kind of good cheating way to do it. And when we run it, we end up getting, good decent results. So let's take a look at some of the problems. Like that was the whole script here. And if I run this, I'll let it run while I'm pulling up some of these other things. It takes a little bit of time. The reason why it takes a little bit of time is every time I'm running this, I'm completely running a new pass through Binary Ninja. Probably should be doing this on a Binary Ninja database to be a little bit faster. But whatever, it's not that big of a deal. So let's take a look at MLIL versus HLIL. I know this video is getting really long, but whatever, you watch it if you want to. All right, so let's take a look at this example. So I'm here, and this is var A0. If I scroll up, var A0 right here. Perfect. Okay, that's easy. We just looked at how to find this correlation. We found it, we alert, we're done. This is on HLIL. Let me switch back to MLIL and show you what we have to do. So now here we're at RDI8. RDI8 comes from RDI or RAX23. RAX23 comes from var A0. var A0 is used here. 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 But it's assigned to this, which is also assigned to this, which is now in buffer. Bottom line is that's a lot of different reassignments. That's crazy. And when you go to high level IL, like it folds it all up for you. This is excellent. There's so much work that you had to do in MLIL to correlate, to just say like, yo, this variable var A actually relates to this guy. And in HLIL, it does like basically all of the work for you. Even in MLIL, when we come here and we're down at like this location, right? Following this up is really easy for a human. You just click on it and keep following it up. Like this isn't hard. And then you kind of like follow your way back down. But if this function was huge and nasty, like hundreds of basic blocks and stuff, that can be really hard to track down. You don't have a monitor big enough. Like one just doesn't exist, right? Like, and you're zooming out and you're trying to find like where the things are highlighted. And it's like, it just gets to be kind of nasty doing it manually, right? So sometimes like falling back to a manual analysis to verify this stuff works really well, and other times it's not an easy task, right? So I'm just rambling at this point. Let's take a look at the other one. This is resolving parameters. Okay, let me look at this guy, and I'll show you another weird thing that happens. Weird from just like a complexity standpoint. It's not really like... Okay, so here. Right, so if I go to this function and I see that printf is called from here, and I go to look at the format, it's a call, right? It's not a variable, right? It's not an addition. Like, what? Like, I had to dig into this guy, figure out what it does, what it returns, just to get a sense of what this might be. I do know that this printf does have a component, which is the argument. And up here, so I can really simplify this basically to this case. There are some things that you want to consider, and right now there's no way that we're going to find this because this ends up being very, very different in HLIL. So if I switch back down to MLIL, now it's just a variable again, right? And then I can track this back to the output of this, right? So you have to keep doing that tracking. So there's like, pluses and minuses from going to a lower level to a higher level, or from a higher level to a lower level. And you'll see lots of really weird things like this. Like, to me, reading this as a human, this makes a heck of a lot of sense, right? This is not a problem at all. But when you're doing it from a scripted sense and you're trying to have like a pattern for looking for issues or problems, this is a kind of a weird thing. Like, if I wouldn't have seen this example, I wouldn't have known to even check if the format was a return value from a call. Like, that's not something that I would have just thought about. So this sense of like, we can write a signature for something as long as we've seen it before kind of sucks, right? Like, I want to be able to write something that can find format string vulnerabilities all the time. But the simple reality is that sometimes there's complexities that you just don't think about, and you're going to miss them, right? So that's pretty much it. Like there's a lot more. There are more vulnerabilities or vulnerable functions inside of this binary that this does not yet find. And a lot of those reasons end up being that there are just some kind of weird quirks or patterns that we have to implement. So let's try to find one that we don't support. So for this one, I don't think we support vprintf, so why not? So if you're running this and you don't see it printing out and you're like, why doesn't that come out? We can try to find out why. So here's fgets. We know we support that. Yeah, okay. So here's what happens is we're assuming that the source and the sink happen in the same function, right? It's for simplicity, and things get kind of crazy when you start drilling down into other functions and then going back up into callers and callees. Like the problem with that is that you don't know where the bounds are, and you can end up traversing a really large binary for a really long time. So there's a lot of complexity in that, right? So in this particular case, in this function, which is bad, if I come down here, I can find a source, right? It's wrapped up into an if, which is another thing that we didn't really consider, is that the if clause actually has this condition that's based on the return value of a function, and then that's based on this. We don't really concern ourselves with data flow or control flow. We can totally do that to try to figure out if things are reachable. But in this case, having to look into an if operation, like we don't support that up here. When we look at this, we're basically saying, is it a call or is it an init? We don't even check to see if it's an if, right? So that's another thing that we have to consider too. So if we're looking at this buffer, what we need to do is try to figure out where the sink is. And it turns out it's in this like wrapper function called bad va sync. And if we dig into that, we see that the first parameter to this guy is then passed into vprintf. So vprintf we should support. There it is. And the reason what we don't support it here is if this were taken out of that and slapped here, we would find this, right? Or we'd be very close to finding it because we just need to implement this if. This is the problem with this type of analysis, is that like there's just so many weird, funky things. But in a sense, like the more general that we make things, the more false positives we're gonna get. But I think the more kind of wide reaching that is. And honestly, we've run this against things where we have hundreds of outputs, and you give that to a reverse engineer who's good and a vulnerability researcher who kind of understands this stuff, and they can validate these things like boom, 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 and tell you, no, this is wrong, this is wrong, this is wrong. This is interesting, let me mark it, and then continue on. And then you generate a short list, and then you start digging into those a little bit more to try to see if they're interesting. And then what you're left with is possibilities, and you can fuzz towards those, you can emulate, you can put more, more horsepower, more brain power on it by getting multiple researchers on that target, and saying like, is this an interesting bug here, or is this just nothing at all? So I hope that helps. I hope that's something that kind of makes sense. Potentially Vulnerable is the place that will have all of this stuff. So just go to 134 and then click on this, and then this is all of it. I think I removed a little bug in here. I'll push that in a second. But if you have any questions, feel free to reach out. Otherwise, hey, thanks for watching.